Hello, this is S&D College of Engineering lecture series for first year engineering physics. Today's topic is about the diode equations. As in previous topics, we had seen about the doping concentration variations, its derivation, and other relations with reference to the PN junction diode. And also we had seen about the conductivity, resistivity of the materials. Now in PN junction diode, as we know, trivalent impurities, by doping the trivalent impurity in a semiconductor, that is fourth group element, we get the p-type material. And if we dope the pentavalent impurity, that is fifth pentavalent impurity from the periodic table, then we get the n-type of material. So elements movement across the junction will be electrons outside the depletion region with enough thermal energy greater than electron volt and barrier potential can overcome the junction barrier. So at equilibrium what happens? The current will be drift. So charges will be drift according to the nature's law. So charges will be drift from the higher carrier concentration to the lower carrier concentration. So electron diffuses across the p side and holes diffuses across the n side. So the magnitude of the current depends on the height of the potential barrier. The thermal current is given by a modified form of Boltzmann equation. So In is equal to A e raised to minus EV upon KT, where A is the constants. So I is independent of the barrier height, that is current ID. It doesn't matter how large the barrier is, electrons will still fall down it. For no applied external voltage, the system is in equilibrium. In other words, there can be no net flow of electrons across the junction. If we are not applying external potential, so it will be at equilibrium. This gives the current I thermal is equal to the current OE. Therefore, so A e raised to minus EV upon KT will be equal to IOE. So the same arguments also apply the whole movement across the junction due to electrons and holes. Forward bias for the p-type positive with respect to n-type. So here again we are getting the IE. In previous there is a current due to O, that is holes. Here current due to electrons. So IE is equal to I thermal minus IOE. So it will again comes equal to IOE e raised to minus kV. So instead of minus kV, here it is plus EV. So EV upon KT minus 1. Now when we apply the reverse bias potential, what happens? The charges, the positive side towards the N terminal and negative side towards the P terminal. So depletion region widens because the charges, instead of whatever may be the charge is depleted, the depletion region is widest due to reverse bias potential. So IOE is the same for zero external voltage and the I thermal is decreased as the potential barrier is now much larger. So again by substituting above in the last, we can come to know that the results can be combined to form the single equation. So IE, current IE due to electrons, is equal to IOE e raised to EV upon KT minus 1, where V is positive for forward bias and negative for reverse bias. Similarly, an equation can be derived for holes. So for holes, instead of IE, here we consider IH and I is the same. And the total current flow across the junction is given by the sum of the electron and components. That is sum of the electrons and holes. So total current is equal to current due to electrons and current due to holes. So here the final equation becomes I is equal to I0 e raised to EV upon KT minus 1. Now if we observe the I versus, that is current versus voltage characteristics, that is IV characteristics. Now what happens? In forward bias, current due to majority of charge carriers. a PN junction allows the large current to flow in one direction but only a very small in the reverse direction. So to consider this and to analyze this, here one example is taken. You can read it and maybe consider it. Carrier transport in a PN junction diode. Now what happens? Hole density in N-type material and electron density in P-type material. So at equilibrium, minority carrier density in N-type material is less, minority carrier density in N-type material is less, and similar is happening in P-type material. What is the value of I/O? Simple analysis, the same result is obtained from more involved calculations. So by using this, here we will get the equation for G, then equation for current. Now more advanced treatment. So by using statistical mechanics and electron and hole diffusion equations to calculate the value of I/O. The equation derived in this lecture adequately describes the IV characteristics of some PN diodes, for example germanium. However, only qualitative agreement is found for silicon and gallium arsenide material. Several factors contribute to this, including surface effects, which gives rise to surface leakage currents, generation and recombination of carriers in the depletion region, series resistance, breakdown effects. Now here is the VI characteristics accurate from principles of semiconductor devices. So the actual VI characteristics, if we zoom it, so you can observe the ideal diode characteristics just like a linear, and for high injection that graph will be bending, and high series resistance it will goes on bending. So reverse breakdown, in the reverse breakdown, as we know, when we are applying the reverse bias voltage, the current due to minority charge carriers, at certain reverse bias the current flow through a PN junction found increases rapidly. This is known as a reverse breakdown because the applied external potential is very large. So there is a reverse breakdown. The size of the breakdown voltage depends on the parameters of the PN junction, except for doping levels. So there are two types of breakdowns, avalanche breakdown and Zener breakdown. So avalanche breakdown. So what happens in avalanche breakdown, that we will see in the next lecture, and Zener diode also. Okay, thank you very much.